Alright, this video goes along with sections 1.5, 1.6, and 1.7. So I just wanted to talk through some of the details of a few of the proofs, give you an idea of what I'm looking for, and then talk about the concept of an equivalence relation. Alright, so this first one is from section 1.5. This example is not in the textbook, so I thought it would be a good one to go through. The goal here is to prove that B is the midpoint of the line segment AC. And that's a bit redundant. I guess I can just say, okay, B is the midpoint of, and then this notation means line segment AC. And we're supposed to prove that AB, the length, equals the length of AC divided by 2. Alright, so even if it's not asked for, anytime you're making a proof having to do with geometry, let's go ahead and make a drawing or a diagram to go along with this. And then this sort of just may give you an intuitive idea of why the statement that you're supposed to prove is true. So for this one we have B is the midpoint of line segment AC. So let's draw a line segment AC. And then we'll draw B on there, and since it is the midpoint, we'll go ahead and put it where it seems to be the middle of that line segment. Okay. So now if you wanted to mark these as congruent, you can do that, but just keep in mind that the given statement doesn't actually say that those are congruent, so that's assuming something that's not given that you would want to include somewhere in your list of statements here. So sometimes what I like to do is just leave off those congruent symbols until we get to the point where that's been proven. Alright, so statement number 1 should always be the given. So we should have B is the midpoint of line segment AC. And the reason for the first statement is always that it's given. Now looking ahead, we know what the last statement should be. It's whatever we're trying to prove. So we want to get to the point where we know that AB equals AC over 2. Right? Now the reason for this can vary. We don't know right now. It depends on whatever the previous statement right before that was. Alright, so now if you're looking for where to go from here, here's a strategy that you can use. I really like this one. So if you are making some scratch paper here or something, make 2 lists, one of what you know and then one of information that you can get starting from your goal and working backwards. So right now we know B is the midpoint of AC. And then our goal is to get AB equals AC over 2. So now you have 2 options. You can work forwards and see what we know because of the fact that B is the midpoint, or we can work backwards, start with the goal, and figure out what would be a previous step that comes before that. All right, so for instance, starting from what we know, B is the midpoint, we can work with the definition of midpoint, or we could work with anything we know about line segments. So not too much we can get from the line segment portion of this, but we can use the definition of a midpoint. So you'll want to have your definitions either memorized or have these on hand, and you may also want Appendix B, all of the different postulates and theorems that you can use. So the rule is you can use anything that leads up to whatever this is that we're trying to prove. Now this one is in section 1.5, so you can use anything up to that point. Now if you go back to section 1.3, you can find the definition of a midpoint. The midpoint of a line segment is the point that separates the line segment into 2 congruent parts. Okay, so that's helpful. And then working backwards from the goal, this is an equation, so start thinking in terms of algebra, like what else you could do with that or what else you know. So a couple different options. One that stands out is the fact that we could multiply by 2, and you could get 2AB equals AC. Or if it's helpful, you could even write this AB plus AB equals AC. Okay, so those are some things we'd have to justify, but that gives us a direction to head. Okay, so let's go ahead and fill in what we know from the definition of midpoint, and B divides this line segment AC into two congruent parts. So we want to say that segment AB is congruent to segment BC. Right? And notice we eventually do want to talk about the lengths of these segments, but the lengths are not actually mentioned in the definition. So you have to state exactly what's given. All right? And then that's the definition of midpoint. Feel free to abbreviate, and you'll see some as we go that are used in the textbook, and anything that you see show up in examples you can do. So def for definition, POST for postulate. You can number them if you like, right? Or if you wanted to give the name of a postulate, that's fine too. All right, so where do we go from here? We'll notice another thing. Right now we're still talking about segments and congruence, and eventually we want the measures or the distances or lengths. So anytime you can switch over, that's helpful. Right? And we can do that right now. We now know that AB equals BC. All right, and why? Well, the reason you're looking for would be whatever justifies changing statement 2 into statement 3. All right, and that one, if you look back, this is the definition of congruence. Okay, so two segments that are congruent have equal lengths. All right, so now working backwards, maybe I want to do that equation 2AB equals AC. All right, and I don't know why I can make that statement yet. I don't have a reason here for 5, but I do have a reason for why I can get from 5 to 6. This is an algebraic reason, so have that handout on hand as well, or look back at tables 1.5, 1.6, and 1.7. Right, so you have some properties of equality, and to get from 5 to 6, what we did is divide by 2. So the reason would be the division property of equality. I'm just going to call this division prop. Okay. You could also say multiplication, because if you think of this as multiplying by 1/2, that would be fine as well. So really the addition and subtraction ones are interchangeable, because subtracting is the same thing as adding a negative, and the multiplication and division ones are interchangeable as well. All right, so we're getting there. Now how do we know that 2AB equals AC? We need to connect that, and right now we have that AB equals BC. So maybe intuitively you can see this, and let's look at the drawing here. Maybe that would be helpful. Okay, so AB is equal to BC, so I'm going to mark those with these little hatch marks to indicate that they are the same length. And how do I know that 2 of AB would equal AC? All right, well, one thing we know, all right, anytime you're talking about segment lengths, if you're stuck, just kind of flip through and start looking at the definitions and postulates, and look for anything that's relevant or seems to be discussing segments and lengths. And you may notice the segment addition postulate. This is number 3. And it says that if X is a point on segment AB, so that X is between A and B, then AX plus XB is equal to AB. So we can use that, we just need to change the lettering. In our example, we have segment AC, and the point in the middle is B. All right, so if we rephrase that for this situation, we would have AB plus BC equals AC, and that's the segment addition postulate. All right, I'll put the name. You could just put postulate 3 if you wanted as well. Segment addition postulate. Okay, now there aren't necessarily 6 steps to this one. Okay, you can add more or less steps. Same for the textbook. you can have some variety in the way that you prove these. But in this case, let's check and see if we are ready to jump from statement 4 to 5. Okay, so keep in mind for statement 5, this is actually AB plus AB is AC. All right, we know that. And if we compare that with statement 4, the only real difference is that this second AB is there in place of BC. All right, so do we have a reason for why we can switch BC with AB? And if you look back at the algebra properties again, there's one called the substitution property. So anytime you have things that are equal, you can switch one out for the other one or replace it in an equation. All right, so some tips for substitution, times when it looks like this, or anytime when it looks like normal algebra, so or just like addition or subtraction. So if I had something like x plus 6 plus 4 equals 20, and then my next line was x plus 10 equals 20, that's also the substitution property because I've swapped out 6 plus 4 with something that it equals. All right, so this is the substitution property as the reason. Right. And we kind of did two substitutions. So you can do this as 2 steps if you want, but it's okay if you want to just summarize and put it in 1 step. So the first substitution was changing BC to AB, and then the next substitution was swapping out AB plus AB for 2AB. Okay, so another substitution of something that's equal. All right, so we've connected this, and you may want to just read through it again and make sure that it makes sense, that everything has a justification, and that it's arranged in a logical order that makes sense. All right, so this looks good to me, and that would be the end of this proof. All right, here's another theorem, and its proof shows up on page 47. So I'm not going to walk through the entire proof here, but one of the other things I wanted to mention was the fact that usually you want to rewrite this theorem in your given spot, and you want to rewrite it using some specific labels and lines and notation and things that we can actually talk about in a proof. So what we're given is if 2 lines are perpendicular and we're supposed to prove, then they meet to form right angles. So we can't just write for the given 2 lines are perpendicular. Which lines are we talking about? And then proving that they form right angles. Well, which angles are the right angles? So what we want to do is just take this first part and make this specific, make some sort of a drawing, label everything that needs to be labeled. So we need to draw a diagram of 2 lines that are perpendicular. All right, so we can do that. And I'll draw these horizontal and vertical, but you could do them sort of on a slant or a diagonal as well. They don't have to be straight. Okay, now one thing you don't want to do is mark like a right angle in here. We know that that's true, but we haven't proven that yet. So the only thing we know is that these are perpendicular. So we'll state that they are perpendicular, and that'll be good enough. And then later on in the proof we can use other facts about perpendicular lines. But notice in this case we're trying to prove that they form right angles, so we can't assume what we're trying to prove. Another difference you might notice is that perhaps in previous courses you may have seen the definition of perpendicular lines as ones that meet at right angles, but in this textbook the definition of perpendicular lines is ones that meet at congruent adjacent angles. Right? So sometimes we flip-flop those and use this as the definition and then prove the other one as a theorem. So it will just, it will differ based on which book you're reading, so it doesn't really matter. We just want to assume one and then prove the other. Okay, so we have our 2 lines, and then we have some options here. So let me give you two examples of how you could label this. We know for lines that we can call these by lowercase letters, so we could call this like line L and line M, right? And now if we're supposed to be talking about angles and proving that these lines meet at right angles, we might want to label the angles. So we could call these, for instance, like angles 1, 2, 3, and 4, right? Or another option, if you want to use the 3-letter notation for angles, then let's actually put some points on these lines. And here's a textbook example, right? So they're going to call this A, and here's a point B, and C and D, right? And then they put E in the middle as the intersection point, right? So since we're talking about lines meeting, it does make sense to label that intersection. So over here on the left, I might also want to label this as well. So we'll call that A. Okay, it doesn't matter what you call that point. All right, so now with those diagrams, let's write the given statements. So if you use the one on the left here, then we need to state that these lines are perpendicular. All right, so I would say something like, line L is perpendicular. There's the symbol for perpendicular. Line L is perpendicular to line M. Okay, and I could say something like that they are intersecting at point A. Right? And that's all I need. That's the only thing we were given. The two lines are perpendicular. On the right, I would say the same thing, just with different notation. So I might say line AB is perpendicular to line CD. Okay? And then here's another way we could say they intersect at E. We could say that we could use the intersection symbol. So line AB intersects line CD, and that intersection is the point E. Okay? So then your proof, you would just be consistent with whatever notation you've used as you go throughout. Now let's write the proof statement. So we need to prove that these lines meet at right angles. Okay, they meet to form right angles. So since we know from the definition that all 4 of these angles are congruent, then it's sufficient to just prove that one of these angles is a right angle, and then it would not be hard to just continue the proof and show that then because these are congruent, then all of the other ones are right angles as well. So we'll kind of cheat a little bit. So this is the given, and then the prove, we just want to show that one of these angles is right. Right, so we could say something like angle 1 is a right angle. Right? Or over here we could say angle, let's see, we'll just choose any one at all. So how about AED? Angle AED is a right angle. Okay. Now notice too, I didn't say the measure of angle AED is 90 degrees because that's not actually the statement what we were trying to prove. Okay, we may use that in the proof somewhere, but we want to actually prove that it's a right angle. All right, let's talk a little bit about relations from section 1.6. There is a formal definition, but we're going to skip over that and just sort of intuitively describe this as connecting two elements of an associated set of objects. So we're talking about like two of the same type of thing, like two angles, two lines, two numbers, and then we want to connect them using one of these relations. Okay, so they're not like operations, but relations are things that function in the same sort of a way as the equal sign. Okay, so that's a way to relate two things. Greater than or is perpendicular to, here's some other examples. Here's a non-mathematical one, is a brother of. Okay, that's actually a human type of a relation or relationship. So an equivalence relation is a specific type of these relations, and basically these are the ones that function like the equal sign, and that's why we call them equivalence relations. So just like the equal sign, they also have to have these properties: reflexive, symmetric, and transitive. So this is something we talked about back when we did properties of equality, okay, and we saw that for the equal sign, okay, and if we're talking about like numbers, A equals A, so 3 equals 3, for example. Symmetric, we know that if, we'll do numbers this time, if 3 equals 1 plus 2, then we also know that 1 plus 2 equals 3. So it's symmetric. You can flip-flop the two sides, the two statements or expressions on either side of an equal sign. And then the transitive property, we know, like if we know that A equals B and B equals C, then we also know that A equals C. So we can kind of make a chain of equal signs. All right. So we want to look at some of these relations that we just described in this table, and we want to see if they have those same properties. So let's look at is less than. So the reflexive property first. So let's look at is less than, and does it have the reflexive property? And here the book is just using this capital R to stand in place of any of these relation type symbols. Okay, so we're just going to fill it in with whatever one we're talking about. So we want to know, for example, is 5 less than 5? Okay, something less than itself. And no, that is not true. Okay, so the less than relation does not have the reflexive property. So right away we know it's not an equivalence relation, but it is interesting to just go on and look to see if it has these other properties. So the symmetric property, we want to know if, okay, now these A and B are two different things. All right, so we want to know, for example, if 5 is less than 8, is it also true, can we flip-flop this? Does that mean that 8 is less than 5? And that's definitely a no as well. All right, and then the transitive property, now we're talking about A, B, and C. So we want to start out with two true statements and see if it implies this third one. Okay, so let's do something like if 5 is less than 8 and 8 is less than, let's do 10, does that also mean that 5 is less than 10? All right, and in this case, this is true. And just really informally, we haven't proved it, but if you, and we can't prove these are axioms, so things that we accept sort of intuitively without proving. But if you think about different numbers and try this with positives or negatives or any real numbers, you will find that all of the examples you can think of are true. So yes, the relation is less than does have this transitive property. So that's not enough to make it an equivalence relation, but it does have that one property. All right, let's try the same thing for is perpendicular to, and we want to test and see if it has these three properties. So first of all is okay, now perpendicular only deals with lines. So we'll try this statement but with lines. Okay, is a line like L, is it perpendicular to itself? Okay, and that's a no. If a line is perpendicular to another line, then can we flip-flop those? Is M perpendicular to L? All right, and this one's the example given in the book. It is symmetric. That is a true fact. And then how about transitive? So if L is if L is perpendicular to M, and M is perpendicular to K, does that mean that L is perpendicular to K? All right, so let's make a little diagram, see if we think this is true. Okay, so here's L. All right, and let's draw a perpendicular line M. Oops. All right, and then we need to draw a perpendicular line K. So K has to intersect M somewhere. I can put it here. and then I want to check, is L perpendicular to K? And in the example I've given, I've successfully landed on one right away that shows that this is not true. And in fact, those would be parallel. So no, this does not have the transitive property. Now there is a way to draw K so that it is perpendicular to L. If I had drawn it, try to picture this in like the 3D, okay, so that those meet at a right angle. It is possible to have that happen, but it doesn't happen every single time. And that's what would need to happen for the transitive property. It would have to always be true. All right, so this is another example of a relation that is not an equivalence relation. If it was an equivalence relation, we would have to have 3 yeses here. All right, and then the last thing I wanted to mention, this is from section 1.7. It gives you the essential parts of the formal proof of a theorem. So we've already talked about the fact that the statement is different than the given. Okay, so the statement, you're just going to, in general, state this theorem. In the given, right, the drawing, you're going to make it specific. Okay, you're drawing whatever the hypothesis is, the things that we're assuming to be true. And then the given, you're going to describe the drawing according to the information found in the hypothesis of the theorem. So the given is where you get specific and mention labels and specific angles and names of lines, things like that. The proof is based on the conclusion of the theorem. Okay, so this original theorem in number 1, there's going to be a hypothesis and then a conclusion. So it's going to be like an if something, then something. So the hypothesis tells you what the drawing looks like and also the given, but the conclusion tells you what you're trying to prove. And then the last piece is the long one. This is the actual proof itself, and you start with the hypothesis and go with the one that's in the given, the more specific one, and you try to get to the prove statement. Now this one says it's an ordered list of claims and justifications. We can also write a proof that's more of like a paragraph format. It doesn't have to be the 2 columns, but at least in this section we're focusing mostly on those 2-column type proofs with statements on this side and then reasons for the statements on this side. Other helpful things to know. The given, you can mention it all at once right away in the first step, but sometimes we also like to mention just a piece of the given, and then we'll come back to another piece of the given maybe later on. So maybe like statement 5, you'd have some more information that was given in the given. Another good thing to know, in algebra proofs, a lot of times you just proceed with each statement following directly from the one before. So we did some examples, something like, if you know 2x plus 3 equals 8, right, then your next step might be 2x equals 5, and then your next step would be x equals 2.5. So each statement follows directly from the one before. In geometry proofs, that's not always the case. So sometimes you can jump around, and you could have, for instance, like statements 2 and 3 both depend on statement 1, the given, okay, but 2 and 3 are not related to each other at all. All right, so just some things to be aware of as you're starting to see some of the ways to write proofs. Okay, that's all I have to say about these sections. You can read through the proofs themselves in the textbook, and then there are also some that are left as exercises, so those might be good things to try on your own, and then we could discuss after you have a chance to look through these sections.